Welcome everyone to the Oxford seminar. This week we're hearing from David, who will be telling us about composing flavoured Petri nets.
Thank you, Jason. It's great to be here at our own seminar. Yeah, I'm going to be talking about composing flavored Petri nets. So Petri nets of a variety of different flavors. Although I will note that this can be even more generalized, even more flavorless. So the big sort of end goal would be to give a nice compositional framework for stochastically and dynamically colored Petri nets, which are actually a little bit beyond what we're going to get to today, simply because they have these things called inhibitor arcs. And so we could talk about that more later, but for now, I'm just going to try and describe a module of systems in this double operatic theory of systems. You can see this paper that Sophie and I put out a few months ago, which is an extension of the sort of work that I had in a manuscript you can find on my website, to a variety of different, as we call them, doctrines. And in this talk, we're going to give another doctrine for these various flavors of Petri net. And so this builds on the work of a lot of people. It's not, it's really more like playing Lego. There's not a big new theorem here. In particular, Jaz Myers, Jade Master, Fabrizio Genovese, David Spivak, and Joachim Koch. So I've listed the sort of ideas that I'm going to be building off of here. So let's get going. Okay. So first, what is a Petri net? Now, I don't really know the history of Petri nets too well. Presumably, they were invented by Petri, although knowing math naming things, they were probably invented by someone before Petri. But the main idea is that they are a graph-like structure, graph-like structure for presenting dynamical systems. So a Petri net is a sort of way to conceptually present the dynamics of a certain situation, and what it means to be a dynamical system in this sentence is going to depend on all the different flavors of Petri net you have, and even what you do with a Petri net once you have it. So, but the basic underlying idea for Petri nets is that you have they're usually called things like you have some species or things, as I might want to call them, and then you have some transitions or processes, or maybe I should say basic processes. And each transition T takes in, transforms some species S1 ... Sn, potentially with repeats, into some other set of species. And so this is the basic idea. You have some stuff, and then you have some ways those stuff can transform, right? And that is the basic idea of a Petri net. So category theorists love Petri nets. So I guess what I should say is that you can take, maybe I should, here's an example of a Petri net. So e.g., the famous SIR model from epidemiology.
So we have three species. S for susceptible, I for infected, and R for recovered or removed. And the basic transition you can have is, so one, we have infection. And what infection does is it takes a susceptible person and an infected person, and it turns them into two infected people. Okay? And then we also have recovery. And that takes an infected person and turns them into a recovered person. So this is the basic SIR model. Now, when we draw this this doesn't look too graphical, right? When we draw this graphically, we might write, we usually write this with we write a transition as a box having some inputs and some outputs. So in this case, infection is a box like this, and recovery is a box like this. Where now, then we also have our species, and we draw these as sort of bubbles. So here's the S bubble, and then I'm going to have to put the I bubble way in the middle here. And now we need to direct these so that we can actually remember which way they go. And then here, the I bubble goes out there, and here this goes into the R bubble. So you would get a net that looks like this, which is a graphical structure of a certain form. Now, I'll tell you, I personally don't like representing Petri nets as graphs. I find it really confusing. I prefer to represent them as sort of just bags of transitions. So just, I'm gonna like do this thing where I just list out all the transitions like this, and maybe I'll write them out instead, you know, as we could write this instead as S, I, and this we could write as I, R, and we just write it like that. So you could display it all in one piece if you wanted to. I personally find that confusing, so I'm probably going to write it like this. Okay. So from a Petri net, you can turn it into a dynamical system. Remember, these are ways to present dynamical systems. And so one of the ways you could do is what's called the master equation, where you associate each one of these transitions with a rate, and then you you associate each one of your species with a real number, and then, or sorry, a real valued function of time, and then you you give a differential equation where you take every species, and you say that its change is proportional, is the sum of all of the transitions that yield it, minus all the transitions that take it away, that take it as input. So in particular, we could write down ds dt here. Well, there's some rate of infection. So just say nothing produces S in this one. So we have a single transition, which is infection, that removes susceptible people, but it's proportional to the current amount of S's and the amount of I's, right? And then the I's have two processes involved, right? They actually get infected times 2, really, I think. Is that right? Maybe I'm doing this wrong. I apologize if I make any mistakes with this part. This is not most of what the talk is going to be about, how you manipulate the presentations and not what you actually do with them.
It would be 2, but you would have a minus there, is that right?
Oh yeah. That's right. I'll let me do it out. That's right. You have a 2, and then you also have the minus RM SI. In total, that's just one of them. Thank you. It's good to be consistent here. And then also we minus out the R recovery, and that's just times I. And then the R dt is just equal R recovery times I. Okay. And so this is known as I believe it's known as the master equation. You see it's sort of algorithmically produced, and in fact, you can even give a compositionality theorem for such things, which I believe Jaz Myers has given at some point, maybe with someone else. I should probably know this better, but I apologize if I'm for forgetting who this is. But anyway, so this is a particular way of understanding the meaning of this. But another way you could think of it is that imagine we had a lot of actual individual susceptible, infected, and recovered people. These, if we had a bunch of these individuals, so this is one semantics here, but we could also have like a bunch of individual blobs here, the S blob, the I blob, and the R blob, and we have a bunch of different individuals in them. And then we imagine this as a system that these things, when they're in here, are called tokens. And we can imagine in different dynamics where you have this set of tokens partitioned into the various species. And then that updates can update deterministically, or sorry, that can update on a discrete time schedule. The other one's a continuous time by picking, say, for example, picking a transition to run at any time step, right? So or maybe you do them all at the time step, or maybe you do it with a stochastic, extra parameter. There's a lot of different ways to do this. So for example, I could choose a susceptible person and an infected person, and then I could remove them, and then I could make 2 new infected people, which has the net result, of course, of just moving that susceptible person into the affected one. And that is the so-called token semantics for Petri nets. My point is to say here that there's actually quite a few different semantics for Petri nets, and I'm not going to talk about those right now. I'm really going to talk about just the Petri nets. So, okay. Next topic is, why do category theorists, and this is going to be important for us, love Petri nets? And the answer, because Petri nets present symmetric monodal categories. And we love those. Okay. So in other words, a Petri net is to an SMC as a graph is to a category. Roughly speaking. And so they show, because symmetric monodal categories show up all over the place, Petri nets are actually secretly all over the place in category theory as well. Okay. So finally, maybe I should define for you. So, okay, so now back to what actually is a Petri net. So there's actually a lot of different ways you could define a Petri net that are very subtly different. And I believe there's an overview paper comparing these by, I think, Jaz Myers et al. Excuse me again. But I'm going to talk about I'm going to give you the definition of so-called whole grain Petri nets due to by Joachim Koch. These are sort of the most nice from a category theoretical standpoint. So a whole grain Petri net consists of a set S of species, right? And a set T of transitions. We put S over here. And then we also have 2 sets I and O. This makes the cetos things, and this is sometimes the CETOS definition, and two spans like this. But with an extra condition, which is that this has finite fibers, and this also has finite fibers. So what does this mean? Well, I'm going to give another translation of this, i.e., this is the same thing as having T, S, S like this, but now we take the category of finite sets and we slice it over S. Maybe finite sets and bijections, just. We're only using the objects here because T is still set, and we give two maps like this, which I can call I and O. And so what is this explicitly? Well, for every element of T in the top one, you send it to the inverse image, I sub T, and then I sub T has this function into S that it gets as a restriction. This is a subset. And so this gets this function, and that's the one I've called I here. Okay. So these two things here is actually the free symmetric monoidal category on S. And this one here is the free symmetric monoidal category on S. So in other words, we can see a Petri net as a span like this. So every transition T in T gets sent to a set of inputs which are labeled in S. That's just something. And a set of outputs which are also labeled in S. So we draw that as T, and then we have here its set of inputs, each one is labeled in S, and this collectively is I, T, and some outputs. And this collectively is OT, this is T, and that is sort of the data I was describing above. So we think of it as sort of a family of these pairs of input and output sets. So it's just the data of these inputs and output sequences like this. Although they're unordered, I'll emphasize that we don't order them. Okay. So now okay, so now I want to talk about the notion of a process in a Petri net. So given a Petri net, a process is a sequence of possible transitions. What do I mean by that? I'm going to first give you the intuition, right? So so it would be something like this. I take a transition that has these two things and an output here, and then maybe I'm plugging it into the back to something that has, you know, 3 inputs, but I don't need to use all of them. I can pass some of them forward, and it produces 2 outputs, and I feed one of them into this one, which produces 2 things, and I feed one of them into this one, you know, which produces 1 thing, but that thing also needs another input, and then I end up with a complicated process like this, multiple in, multiple out. Okay? So this is an example of what a process is. And I'm gonna go into how we do it, but I'll say that as a definition, this is a uniquely defining definition, but not a construction, right? So a definition, but not a construction. I'm going to tell you the universal property that processes should have, and then we're going to actually go through and construct an example of this. By the way, Joachim Koch is a really beautiful construction of this in that paper, the whole grain Petri nets paper. That's not the one I'm going to do right now, but that's a really great and highly combinatorial graphical one. It actually produces these, it shows how these graphs arise in a really nice way using the CETOS formalism. So definition. So if a Petri net P is this thing, then what we'll call proc P is the free symmetric monoidal category generated by P. But I'm actually going to say that really what we're going to get is actually a symmetric monoidal double category. And we'll see how that happens. That actually is what Joachim Koch gets as well. So, because he produces a Siegel groupoid, which is in fact a category, a double category. A symmetric monoidal Siegel groupoid. That's in fact a symmetric monoidal double category. But we're going to just do symmetric monoidal double categories. So the approach that we're taking here is very similar to the approach that Jade Master takes in the second cited paper in the first slide, but she uses a stricter version of this argument, and we're using a up to isomorphism version. But it's the same fundamental idea. So how are we going to do this? Well, we're going to start with this thing here, SMCS to T to SMCS. This is IO, right? And we note that these are SMC here is in fact the free symmetric monoidal category monad on cat. We're applying it to these discrete categories or these sets, right? But still. So the first thing we can do is we can Kleisli extend this. We can Kleisli lift to get SMCT to SMCS, where this is now the lift, the Kleisli lift, and these are both tensor preserving maps. So this is in here, this is taking place in cat, but this is taking place in symmetric monoidal cat. Symmetric monoidal cat. Right, so now we have this graph internal to symmetric monoidal categories, right? So this thing is in, this whole thing here is a graph of SM of cat. So then what we're going to do is we're going to take the free category. Maybe I'll put a pseudo in here. The free category, which will give us something in cat SM of cat. And what will that be? Well, it's going to have the same it's going to have the same feet, which is SMC, SMCS, SMCS, but then it's going to have something else up here, and this is going to be the monoidal category, the symmetric monoidal category cat. It's really a groupoid, as it will end up being a groupoid of processes. And then altogether, we have something here, which is a category internal to symmetric monoidal categories by the wonderful Arcor-Bork-Co symmetry of internalization result. This is the same thing as symmetric monoidal categories in categories internal to categories, which is a symmetric monoidal double category. Okay, so let's look at what that question mark is. The first thing I'm going to note is that every process can be split horizontally like this into things that can happen in sequence. And any one of those things can also be split vertically into two parts. So one thing I'm going to note is that remember by symmetry, the wires can come up and they can pass through. So I'm going to do this, right? So they can split horizontally, each one can be split into two parts like this. These other ones actually aren't split, but for fun, I'll put this here. So each process can be put into an array where what you have is some list of transitions, or really I mean finite set of transitions. Similarly, up here, this is a finite set of transitions, this is a finite set of transitions, this is a finite set of transitions, together with some finite set of species that just pass through. So here's the set of species that pass through. It's all of these. And then I just threw this one on the end so that you could see that it could happen at any stage here. Right. So what we'll see is that if I go down here, and I'm gonna copy this over, go to the next page. Right. The first thing we're gonna do is we're gonna use Lax approach. Well, Lax-Deboux's approach to free monoids. So the first thing we note is that which we can then piece. So what we're going to do is to take the free monoid in graphs with the fixed edge category to be SMCS, right? So the first thing we're going to do is so I'll put SMCS over here. As in, it's a graph, but now we're fixing this one so that we end up with this having a monoidal structure, which is tensor product. The monoidal structure is given by pulling back over SMCS, so composition of spans. So an internal category, I should say, is a monad in span, which is a monoid for pullback in span, right? So this is our pullback here. I sometimes like to put the bottom, just use a bottom out thing for shorthand, so I don't always have to write that SMCS. So this has a monoidal product here. The first thing we're going to do is take the pointed things in here. So we're going to freely adjoin a point. What does that mean? Well, we're going to take SMCS, and then we're going to take the coproduct with SMCT in here to SMCS, SMCS. And this one here is a pointed object of that thing. So we freely adjoined a point. What is the point? Well, the point is this half, the inclusion here. Now, this is a point at which I'm going to say, by the way, SMC is already a free construction, and this is a coproduct. So we're taking this is equivalent to SMC of S plus T. So it's finite sets labeled in S or in T. And you can see that up here, if I go back, that each one of these vertical sections, right? Each one of these vertical section is a finite set, which is consisting either of a transition or of a species. So next, what we're going to do is let me give this an intermediate name. Let me call this one Y. And let me call the inclusion little y. This is notation straight from Lax paper. So what is the inclusion? The inclusion, by the way, is the inclusion of this half. So the way to think about that is that these are representing non-transitions or identities. So this is like the inclusion of identities. Okay. So then what we do is we're going to form this diagram. Right? So first of all, what we're going to do is we're going to take, by square here, I mean really y semi-direct product, tensor pullback y. So an element of y squared, as I'm writing it here, which is y pullback y, is a, remember y here is a family of species and transitions. And that's something that could be here. Y squared is a sequence of is a pair of these, like this and this, that agree on their boundary. So y squared is something of this form, which I have two of them, and y cubed is something of this form. So first we write all those out. But then we note the following sort of equation, right? Which is that if I have here, this transition is here, right? But the process would be the same if I had slid it back. Oh, there's a lot to write. If I had slid it back into here, right? And now you see, what is the difference between those two? Well, it used to be over here, and here was a wire. But now the transition is here, and here is a wire. So we can see those as two different inclusions of y into y squared. One, which is we introduce the identities on the left, and the other, which is we introduce the identities on the right, and those have to be equal. Okay, and then if we had a third way that it could happen, we could slide one. If I put a box all the way down here, right, it could slide all the way across. So we have to do it again for threefold things, and so on. And so we define procedures proc one, this thing is equal to the co-limit of that diagram. Over of this diagram, I mean. This is filtered, symmetric monodal categories is finitary, so it can pullback commutes with this filtered co-limit. So this actually does give you the construction of the free monoid. So also you can just see that is what we're doing up here. So by the way, my conjecture here is that this gives you the same thing as what Joachim Koch's approach, which feels quite different, does. They both, by the way, give you internal categories in symmetric monodal groupoids. So like they're producing the same kind of thing. You don't have to. My claim is that they're literally the same thing.
I have a question.
Yeah.
So there we talked about just finding that one box between two different spaces.
Yeah.
We had a bunch of stuff going on above that box.
Yeah.
Is that something to do with these co-limits being preserved by the by pullbacks?
By pullbacks.
Okay, that's saying if you like add a bunch of stuff above and then do the slide, or do the slide and add the stuff there, that should also, like, you should be able to do the slides and just stuff components of your diagram.
Yeah. And the quotient should be preserved even in that modularity. So it's like sort of saying that you have this, the preservation of co-limits is about sort of this vertical modularity. I could cut even between two processes like this, and sliding above that cut or below that cut is the same as, sliding. It's an interchange law. Yeah. Totally. Okay, cool. So this is all sort of off the shelf stuff. However, I think this is a rather nice presentation of this. By the way, I will note this. I think you can do this not just with SMC, but with FAM, the free product or co-product completion, which acts the exact same way, has the same objects as the free SMC completion on a finite set, right? On a set. But if you do it that way, you'll end up not with a symmetric monodal double category, but actually with a Cartesian double category. And I think you can do that. And all you need to know is that that's also a finitary end of functor, and therefore it should work. I'm a little bit cagey about these, and I'll also tell you that there are real to do this truly honestly, there are some subtleties that I'm brushing under the rug here. And bonus points if you can find them. Okay, so as a takeaway, we have Petri to proc to a symmetric monoidal double category, producing symmetric monoidal double categories with that. Now we also should have a form of forgetful functor going back. And it's not totally true that we do, because Petri nets are kind of restricted of this form. But we have, this should be a relative adjoint relative to the inclusion of Petri nets into graphs of symmetric monodal categories, for which we have. So we have a graph of SM's cat, and we have an adjunction. We have this here. And then we have this here, and that should be our inclusion. Okay. I just want to say that the point being now, so the point is that we can define a map proc of Petri net to some double category. My double categories are always going to be blackboard bold, right? Can be defined. So this is a symmetric monoidal pseudo double functor, or strict if you strict to taste. Nothing will terribly depend on this in this. Again, I'm going to be a little loose with some of these details, and you can iron them out at your leisure. Can be defined on can be defined by sending every species maps to, let's call this F, some object in here, and every transition T, right, which goes between S1 dot 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 Sn and S1 prime dot 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 Sm prime. Again, these are really unordered. Oh. Goes to some map here where we have the tensor product over I of F Si to Ft, and it's a loose arrow here into the tensor product over J of Fsj. Right? In other words, to define a double functor of this form, all you need to do is say what the species get sent to and what the transitions get sent to, but the transitions have to get sent to loose morphisms of the appropriate signature, and that signature is given by the tensor product over their input wires, the tensor product over their output wires, where, remember, we're C here is some symmetric monodal double category. All right. So this is just what it means to have three things. And again, I'm sort of framing this as this is why category theorists like them. We love symmetric monodal stuff. I personally love symmetric monodal double categories. This is how you present free symmetric monodal double categories. It's pretty great. Okay, so let's get back to why everyone else likes them. Everyone else likes Petri nets because they're a great way to describe systems, their behaviors, but the descriptions I gave above were a little limited, because very often you want some other conditions. So let me flip back a few slides, back to our things here, right? So now there's usually some other conditions. Remember, in our token semantics over here, we assumed that we had a bunch of tokens of each species, and every transition was enacted by actually moving the tokens according to the transition, what it says. But sometimes you want to say, actually, that should only happen if some other condition is met. For example, these tokens maybe are little people, and they're little people that live in actual little places. And yes, a susceptible and an infected person come together to make it to infected people, but only if they actually come together. So we should only allow that transition to fire if the actual locations of the susceptible and the infected person are actually close enough that there could be an infection relation, right? And again, if there's also extra data, like that the transition only fires, you know, at a certain chance, that chance might be affected by the nearness of those tokens. Right? So the extra data that one puts on these tokens, or in other words, in general, associates to the species of a Petri net, is known in the literature as a color. It's a color, and the conditions that tell you whether or not you're really allowed to make a transition, that can look into the colors and see something special about those colors, are known as guards. Okay? But then there's also other things. Maybe your people are not just in locations, but they're actually moving around through those locations according to some kind of decision process or whatever. So now it's not just that they have a location that the guard can check to see whether or not the transition is going to fire, but in fact, locally, each of these bubbles is actually updating. Each of these people are walking around in some place, and maybe they actually come close enough together, and then they hit the transition, right? And so that is called the dynamic Petri net, dynamic colored Petri net. People sometimes say guarded Petri net, by the way, if you just have guards, but like there's a lot of there are a lot of letters that get put at the beginning of Petri net. You know, then there's other things, like maybe the transitions actually take time to occur, right? Maybe you become susceptible when a susceptible and an infected person meet. It's not that instantly that susceptible person becomes infected. It's that over the course of a week, there is a probability distribution that at any given day they would test positive. That's really what we know, right? Like you hang out with someone who's coughing in your face, and then within the next few days, you probably come down. But it could be 5 days, or it could be 1 day. You don't know. That's called a stochastic delay transition. And so in general, you start to see that there are lots of different extra bits of data we need to associate to our Petri net to be able to actually produce the model that's above and beyond the graphical structure that I've described so far. So my claim is, and by the way, this claim originates due to Fabrizio Genovese and David Spivak in essentially, I'm adding only this double categorical aspect to it. My claim is that I should say all that extra data you want to put on the Petri net, that's what I mean by flavored Petri nets. That is not that's a term I invented as far as I can tell for this talk, because I didn't know, like I could have called them alphabet soup Petri nets, right? Because there's all the letters that people use. But I'll call that generally the flavoring. So my definition here, so a flavored English spelling Petri net is a symmetric monoidal double functor F, which is the flavoring, from proc P to C, which is the double category, full category of colors. Okay.
Not flavoured, so.
The choice of C determines the flavors.
Okay.
But its objects are the colors.
Okay.
So I was right. And now, so that this definition, by the way, is roughly speaking, since to define a flavoring, as I just have above, you only need to say so in other words, just interpreting this, we send every species S gets a color F of S, right? You could maybe change this around and call it C into F instead, or whatever. This is the kind of thing that I like to spend all my time on, but I'm gonna do math. And every so this here is the color, and it's some object, some mathematical object. I'll go into examples very shortly. And then every transition gets a loose morphism in the double category of the above form. Right? And so note that there's nothing in this that actually uses the type morphisms of the double category C. So if you read that paper by Fabrizio and David, what you'll see is that they just define this in mapping into a symmetric monodal category. They define I don't remember what the name they use there is, but let's say flavored Petri net in that way. It's the same definition fundamentally. However, one thing I'll note is that the C's are actually very often double categories of spans of some sort, which we'll see very shortly. Therefore, it's sort of natural to consider them as double categories. And secondly, the notion of morphism of Petri net, of flavored Petri net, requires the tight structure. So now I'm going to say a morphism of flavored Petri nets is a triangle. So here's proc P, proc Q, C. By the way, they all have the same, we take morphisms for the same coloring double category, right? Together with a tight transformation of this point. So here, I'll call this I'll call this one F, and I'll call this one F bar. So here, there's a choice to make. Is the F just a general symmetric monodal functor, or is it one of the form proc? I'm going to make the choice that it's of the form proc of F, because as a category theorist, that's just like what this, like that's what if I said the obvious morphisms, that would have to be this one. So I'm going to do that. It depends, it changes what you can do with a morphism, but right. So I'll come back to that because it's actually quite nice. Yeah, it's quite nice to not do that if you want for the reachability semantics. But anyway, all right. So this is actually gives F, if this is F and this is FP and this is FQ, this gives FP of S to FQ of F of S, right? And it gives a square like this, FP, or like tensor over I, FP of SI to tensor over I, FQ of F of SI. And then this is FP of T. This is FQ, Q of F of T. Of P S J prime. Insert FQ F. Right? So F, this is F bar of S, and this is F bar of T. So this is the data you need to define a morphism of flavored Petri nets. And this is where the double categorical aspect of C really shines. So, okay, my proposition to you is that, so what I'm going to do now is, one, I'm going to go through examples of these. Two, we're then going to talk about the double operatic theory of systems of these, and that'll be the talk. I'm worried that I'm going to go already over.
We go.
I don't know.
10 minutes.
10 minutes. I'm screwed. Let's see examples. So, for C is equal to squares of sets, we get the ordinary token semantics. So these are colored Petri nets. Why? Well, we assign a set F of S in set is the set of colors. And then every I hope I'm using this terminology right here. And then for every transition, we get a product, we get a function of this form. Which takes a bunch of and maybe this should be just called the token semantics, but it takes a bunch of it takes a bunch of tokens of the species Si, which together with their colors, and it tells you how to produce the new colors of the resulting token. Right? What if we did instead the Kleisli double category of the maybe monad? So this is equivalent to spans where the left leg is mono, of set where the left leg is mono and the right leg is anything. I'll write it like that. So now we still have a set of colors, but now we have here is FSI, and then we have a partial function, but I'm going to write it as a span. Technically, f of t is this whole span, but I'm writing it this way. So now what you see is that we have associated to every transition, not just the transition function that tells us how to update the colors, but also a subset of the colors of the domain that the transition is going to actually need in order to happen. And this is known as the guard. So these things are going to be guarded Petri nets. Let me talk about representability for a moment here, right? Consider the following simple colored Petri net, where we take P is equal to be this single Petri net. So S1, S0, S1, and T. Just all this. And the map we get into set is F of S0, or how about I give it really simple names. 0, 1, and 2. So f of 0 is going to be a singleton containing 0. F of 1 is going to be a singleton containing 1. And f of 2 is going to be, well, in this case, it has to be the unique function, right? So what is a map from there into another Petri net? And this is a case where I start to regret my decision to say that this is of the form proc over here. Maybe I should say that maybe you can see that I can actually make one of these that's like for any list on the left and right. For any n and m, I'll call it T and M. Really, any two finite sets, but T and M is going to have 0 I and 1 J for all of those, and they're all going to be for I going to 1 to n, So this is n many, and this is m many. Let me do it this way. And then a map from that into a Petri net, right? So from T N M, and that's going to be my coloring here, which I'll call 1, into square set. A map from this into, well, proc of this. By the way, proc of that has nothing else going on in it, at this point on. So proc of P here, proc of something, I'm going to call it T. Why? Because a map from this Petri net here to another Petri net just picks out a transition of that arity. Right? So the maps here are in bijection with T in P of that arity. Right? N in M out. A map here, right? What is that? Well, it's a square in this category. So we have 0 here. 1 here. And or like, you know, it's the product over I of 0i and the product over 1 over j of 1j. And here is the single function. Doesn't really do anything. Those are all 1 element sets up there. But then for every 0i, we get an element in over here of f of si. So here is what I'm going to call ci. Or like, sorry, if I get a little f and f bar, I'll do that, and then sorry. This is a little bit of what we call f bar. Or maybe I'll give them other names. Excuse me, sorry. I'll call this S and I'll call this C. There we go. That's a little more. So now the SI, sorry, I already called that proc T. The value of this I'll call SI under T. So I'll define SI is defined equal to proc T 0i. So that it appears down here. And then here, I'll call this Ci. And here is the product over J of Cj, product over F as, of Sj, whatever. And then here is the transition, Ft. And this is a square, which means it has to commute up there. Right? So what that says is that you see a map of Petri nets from this one into there is an actual bunch of tokens together with colors that actually transition into the next bunch of tokens together with colors. So it's a single step transition. And of course, building up more of these, we can see that we're recording the various kinds of transitions by mapping out of these simple Petri nets and simple colors. Down here, if we did the same trick, it would be now, right? We would actually have to add the guarding. So we could have this thing down here. But now we would have the guard. But the guard, by the way, I'm going to take to be the identity here, as in, you know, there's not too many choices there. And the guard here, I can take it to be, again, the identity. And then for this to be a square means that there's a map here, which means that under this transition, the things in the left here, the CI, had to actually satisfy the guard. They land in the guard, right? Because this is the same thing as this, or like, you know, this is the same thing as this, but yeah, okay. Here's another thing I'll note. By changing the double category at the end, we can also change what we want to happen. Let's suppose there's a notion known as inhibitor arc in these, which I haven't talked about. But let's say that we actually marked some of these as inhibitors. So the usual way you do that is you put anyway, let's say let's say you had, some of these were inhibitors. They usually write it like that. And they just come out. So what does an inhibitor mean? Well, something cannot be there. if I change this category so that this has to be a pullback, and then I change this domain so that it actually only takes in the set of I forget what they're called, but like exciters. As in, this is the thing that indicates whether or not you're an inhibitor, right? And we make that the kind of morphism, which is known as an atoll map, is a perfectly normal kind of morphism to take here. Then what we're saying is that you have a bunch of tokens, right? And only the ones that are exciting are in the guard. And otherwise, they're not in the guard, which is the behavior you're supposed to get for that semantics. Okay, next, suppose that C is, let's say, span manifolds, open inclusion, all, and then we foot replaced along ODE to manifold. So foot replacement is the BOFF factorization for double categories. See Kenny Corser's thesis for an explicit construction of it. But what this is now is that we have a bunch of manifolds, pi I F S I. We have an open guard here. You could make this half. You could again, you can have complete freedom over what you choose for C to V. So if you don't like any of the particular choices I'm making here, do not. We just make a different one that works better for you. Okay. F, J, F, S prime J, right? Now these are manifolds, but we also adorn them here with, in fact, a bunch of tangent vectors. And similarly over here. Sorry, I said tangent vectors, but I mean vector fields. And what is that? Well, that's the thing I was talking about earlier, where now the colors form a manifold, and we actually have dynamics at each place. And there's nothing here that requires this. This is foot replacement can be done along any symmetric monodal functor. So there's nothing here that requires that they be ODEs. They could be PDEs. They could be stochastic differential equations. Again, it doesn't matter. But as long as you have a representable semantics for whatever kind of system you're just doing this with, you can still build representability in the above way, because now what we're going to do is a more interesting thing, where this is going to get sent not to the product over the 0 ones. We take a different one. We send this to a product over some interval, product over, AI, BI, some intervals. In order for this to be open, you should pad these by epsilon. Again, I'm going to get lazy here because I'm way over time. The differential equation you put on these is the constant one at 1, which is ddt equals 1. Here, the guard is going to be, again, you need to pad this to be open, but it's just going to be the set of the BI, as in the final endpoints of all these intervals. Padded so it's open. All of these are actually open intervals for small epsilon, whatever, it doesn't matter. We're here, and this one is going to jump to the this is going to be the BI, and this is going to be the AI, as in we're going to jump into the so here we have to pick. There's a lot of different ones because we have to pick the different lengths, right? Each one of those is the length that we're going to stay within each transition, right? And then when we look at this map here, these have to be maps of vector fields, which means that these things here, the CI we have, actually have to be solutions of those differential equations that end in the guard. They then transition by jumping into the beginning of the next solution. And that's what so this is what this square up here would say that it's a solution of the differential equation. This square says that it ends in the guard. This square says we begin the next solution by beginning at the end of the transition. So this is the notion of behavior for dynamic colored Petri nets. Dynamically colored Petri nets, as they're known. What if you want transition times? Well, just add that information to the loose morphisms of C. You need to, if the transition time is deterministic, you can just join a number and then add it compose. If it's stochastic, you need to get a little more clever, right? But in general, the main idea I want to say is that you can do this. And so the final thing I'll say that is that we get a doctrine, a dots doctrine, SMDBL to symmetric monoidal loose right modules, which is our target here. And it's defined in this way. It is C maps to the following symmetric monoidal loose right module. We take quintets in the two category of symmetric monoidal double categories. We flip the direction of the arrows, and then we map out of C. So I didn't actually talk about composing these things the whole time, but this definition contains the composition. I don't know. Maybe I should, I don't know. Should I stop? Should I go on?
We might need to, what can you say in like?
What can I say? So this includes a definition of compositionality where we also take P to proc Q, F to C, and then we get the composition like this. And I'll note that this is not the only kind of doctrine you can make this way. You can also use, you can also do something that's more like the open Petri nets, Jaz Myers, Jaz Myers one, and use co-limits to give a more co-spanning version of this, but where then you have to fix the feet to have particular choices of color within that flavor, and you go over that. But either of them work. They give you two different kinds of composition. This is what I would call nesting composition, because you take a transition here and you sort of fill it in where this becomes decoupled into a bunch of things. This is a bundle, not a copy. This is not a copy. This is bundle of wires, not a copy. And then you send it into a bunch of internal, little things in Q, and it comes back out maybe. And then the composition of these symmetric monoidal double functors just aggregates the colors and all the behavior and stuff in the appropriate way. Yeah, I guess that's it.
Okay, David for his talk. Are there any questions?
So like the guard, is it like a morphism in C or like?
Yeah, so if you have, in general, in general, I would say that that C should be understood like this. The objects are the colors, right? The loose morphisms are whatever a transition is going to do and all the data you need to know about the transition in order to do it. So that includes the guard, that includes the delay, that includes all the other things you need to actually do the transition. It includes where what colors go to which colors, right? So in general, when you're building C for your particular flavor of Petri net, what you want to do is you say, first, what is all the extra data I need for my species? That's your colors. Those become the objects. Then for the loose morphism, you say, what is all the extra data I need to do a transition and understand what that means? So that would be like what are the guards? What's the delay? Where do my transition ends up? Like, is it stochastic? Is the delay stochastic? Is the transition stochastic? Is, whatever. And that becomes the loose morphisms. The type morphisms in both cases should sort of be the natural homomorphisms of whatever you just put down. Yeah.
Sorry, this dots doctrine, is is that consistent with this idea that these vertical maps between the process categories for Petri nets should just be like properly?
Sorry, I should it's had to be.
Okay, yeah.
There we go. And where we see proc here as going from Petri is sort of the is going from Kleisli double category of proc to SM so to quintets of SM double.
Okay. So classic, does that mean when?
Of SM the Kleisli
Oh, right. So the vertical things are the free.
so
Uh,
yeah, where the vertical things
yeah,
are the free ones, yeah.
okay.
So that's how you would type it, and then you have to observe that this is symmetric monoidal. The symmetric monoidal structure is coproduct, which is also product.
Right.
So what that means is that the way you can put multiple together is by it's I would describe it as a simultaneous parallel product, as in all the things run simultaneously and in parallel.
Right.
And then the compositionality you get is that for any process in the domain, for any transition of the domain, you associate it to a bunch of simultaneous processes in the composed systems that you're going to nest and compose that way.
Right.
So that's sort of that's not the only way. That's not the building up Petri nets as graphical structures by colimit. Which you could also build another one of those using the sort of the coast if you have the appropriate pushouts. But yeah.
Could you scroll a little bit to the SMC cursors and stuff?
Up all the way to here.
Yes, the SMC double categories.
Yeah.
Yeah. Okay. So like, briefly, how is this related to the Siegel viewpoint?
Right. So a Siegel object is a Siegel object is a simplicial object that satisfies certain limit conditions, which say that it represents an internal category. So a Siegel object is just the same thing as an internal category. In that sense, like these are all groupoids. So you end up with a Siegel object in groupoids, which is an internal category in groupoids, which is a certain kind of double category. It's a double category where all the tight morphisms are isomorphisms.
Oh, I see.
Right. And so I guess that wouldn't, if we did this for Cartesian, if we did
that would no longer be true. Yeah, it would be a Siegel category. Yeah. And I think it would work there. And the nice thing about that is that all the C's I wrote below are actually Cartesian. And it seems to me that that's a pretty common case that you end up with a Cartesian double category. And it's nice because being Cartesian is a property of a functor as opposed to structure. So there's sort of a nice kind of weird thing there.
Right.
It comes down to the same thing. You just say what it does on generators and relations, but there's something about that where you get extra, you can get extra morphisms, I think, because you could allow for things to sort of map into duplicates. I'm not exactly sure what it does, but I'm interested. I'm interested in knowing what it would mean to take the free Cartesian double category, because Cartesian double categories have symmetric monodal loose bicategories. They aren't like Cartesian every direction. They're just Cartesian in a tight direction. So you still end up with this symmetric monodally stuff that you're expecting for your Petri net. It's just that in the tight direction, you now have duplications and deletions. So you have this sort of meta theoretic duplication and deletion, but object theoretic, you're still linear monoidal.
Okay, we might have to stop it there.
Yeah, sorry. Maybe I'll have to pick up. Maybe I can pick up and do an actual something actually about the composition of these, if there's any more.
Yeah, that'd be interesting. Yeah, but otherwise, let's thank David again. Yeah.